So in the second part of our fifth video, we will be looking in more detail at the friction force. Just before we begin, I would like to say that there are some excellent videos, including some simple classroom experiments by Joe Wolf. I was intending to directly use his videos, with his permission, but there was a reasonably interesting technical difficulty that made that almost impossible. So my friction videos are very much based on Joe's, and I would still recommend watching the originals, which I've included in the resources page. So let's have a closer look at our poor old drudge trying to shift the bookshelf. Underneath here, we have two graphs. The top one in yellow is showing the force our drudge is applying over time, and the second in blue is showing the speed at which the bookshelf is moving forwards. So when the man starts pushing, nothing happens. The bookshelf remains resolutely stationary, and I'm sure we've all encountered this phenomenon. So he pushes harder, he increases the force he's applying, and he does so until the bookshelf starts to move, which it usually does with quite a bit of a jolt. Once the bookshelf is moving, he doesn't have to push quite so hard, and the shelf will slide along quite happily at a reasonably constant velocity. So there is a point at which the bookshelf will start moving. And we define our two types of friction based on this point, so based on whether the two surfaces are moving relative to one another or not. If a force is being applied, but there is no relative motion, so in our case, if the bookshelf is not moving, we're dealing with static friction. And once we have relative motion between the two surfaces, so once the bookshelf starts to move, we are then dealing with kinetic friction. And over the next few slides, we'll look at each of those. So first up is static friction. Static friction is when there is a force applied, but there is no relative motion between the two surfaces. So we're dealing with this section of our graphs. So I'm sure you've all noticed that the heavier an object is, the harder it is in general to push along the floor. So if we take our bookshelf, if I was clever or slightly less lazy, I would have emptied it before I moved. So if we look at the forces acting on our bookshelf, there are four. There's the weight of the bookshelf acting down, and then the normal reaction force acting up. Since the bookshelf has no velocity or no acceleration in the vertical direction, we know that the total sum of the vertical forces must be zero. So we know then by Newton's third law that our normal force must equal to our weight force. Then we have our applied force and our force due to friction opposing it. So while the bookshelf is not moving, this force due to friction must be larger than our applied force. So we push harder. And at the point just before our bookshelf starts moving, this is the limiting case. So we call this the limiting friction. So at this point, our applied force is exactly equal to our friction force. So we can measure both our normal force by measuring the weight of the bookshelf and our force due to friction by measuring the applied force. So if we do that for a number of different weights of our bookshelf, we find that our static frictional force is proportional to our normal force. So we call this constant of proportionality between the two, the coefficient of static friction. So static friction covers the case where our object is not moving. So that means it covers the case from when the applied force is equal to zero, right up until our limiting case. So our coefficient of static friction covers a range of cases up to and including the limiting case. So that means our coefficient of static friction is given by the inequality less than or equal to the force due to friction divided by the normal force. So there is a nice method that we can use to figure out what the coefficient of static friction between two surfaces is. We know that our coefficient of static friction defines the point of equilibrium, so that's the point just before our applied force overcomes the force due to friction. And we know that apart from applying a horizontal force, we can also get an object to slide over a surface by tilting that surface. So if our bookshelf is sitting on the ground and we do nothing to it, there will be no acceleration and nothing will happen. If we increase the angle of our surface of our bookshelf is on, so for example if our bookshelf is sitting on a ramp, then there will be an angle of the ramp at which the bookshelf will slide. And we call the angle just before this happens the critical angle. So that is, on a slope at the critical angle, our object will be in equilibrium. The applied force due to gravity acting down the ramp will equal the force due to static friction acting up the ramp. So once again, we're at the point just before our applied force overcomes the force due to friction. At the critical angle, we're at our limiting case. So clearly, the coefficient of static friction is related to the critical angle. Now we can derive this relationship, but I will not do so here. I've left that as a tutorial question for you. But what we find is that the coefficient of static friction is equal to tan of the critical angle, and that it is independent of the contacting area between the two surfaces. Our second type of friction is our kinetic friction, which occurs when there is relative motion between the two surfaces. So we're looking in this region of the graph now. So where static friction is acting to oppose the intended motion, kinetic friction is acting to oppose the actual motion. So if we do the same experiment as previously, but instead we look at the force required to keep the bookshelf moving at a constant velocity. So at a constant velocity, the acceleration of our bookshelf is equal to 0. So that means that the net force acting on our bookshelf is equal to 0, which means that our applied force is once again equal to our force due to friction. But in this case, we're now dealing with kinetic friction. So as we increase the mass of our bookshelf, we find that the required force also increases, or the weight, and the relationship is linear. So it's related to the weight force. In this case, the slope of the linear relationship is smaller than that for the static friction case. So once again, we have that our force due to friction is proportional to our normal force. In this case, we call our constant of proportionality the coefficient of kinetic friction. In this case, there is only one situation in which the bookshelf moves at a constant velocity, which is when our applied force is equal to our friction force. So our coefficient of kinetic friction is an equality and given by the ratio shown. And that concludes our adventures into friction.